All right, it looks like we've shooed everyone away from the food and in. Microphone good enough? People can hear me? Yes, okay. Well, welcome everyone. Thank you for joining us for the 2024 Gilfillan Memorial Lecture. I'm Eleanor Feingold. I'm the Dean of the College of Science. Tonight we have the privilege, really, of hearing from one of our esteemed colleagues, a trailblazing scientist in experimental physical chemistry. I'll say a little more about our awardee tonight, but first I want to welcome those of you joining us both in person and remotely, including colleagues, alumni, and friends, members of our broad community, and quite a number of members of the Gilfillan family here tonight. Thank you all for joining us. I also want to start by giving thanks to the Research Development Unit and the review panel of College of Science faculty who reviewed all of the nominations for this award and chose tonight's winner. Let me begin with our land acknowledgement. Oregon State University recognizes the impact that its land grant history has had on indigenous communities in Oregon. We accept responsibility for understanding the continuing impact of that history on these communities. Oregon State in Corvallis is located within the traditional homelands of the Marys River Band of the Kalapuya, who were forcibly removed to reservations in Western Oregon. Today, living descendants of these people are part of the Confederated Tribes of the Grand Ronde Community of Oregon and the Confederated Tribes of the Siletz Indians, some of whom are a part of the Oregon State community today. We deeply value their presence and ongoing contributions to the university and to the College of Science. It's our privilege and responsibility to support the success of students from Native and Indigenous communities throughout the United States. The Gilfillan Lecture, a long-standing tradition in our college, brings us together every year to celebrate outstanding science at OSU in honor of Doc Gilfillan, whose record of extraordinary science has positively impacted generations. Francois Doc Gilfillan served as Dean of the College of Science for nearly 25 years, from 1938 to 1962, and also served as acting OSU president from 1941 to 42. The Gilfillan Memorial Award honors Doc Gilfillan's life and recognizes his extensive service and contributions to OSU and to the field of pharmaceutical chemistry. His legacy continues to inspire us, and we're grateful to the Gilfillan family for establishing the award and the lecture. I am very honored tonight to introduce Chemistry Department Head and Professor Wei Kong as our 2024 recipient of the Gilfillan Award for Distinguished Scholarship. This award recognizes faculty in our college who have demonstrated a long and exceptional scientific career with nationally and globally recognized scholarly achievements. An innovator in her field, Wei fearlessly explores unconventional paths. Her journey in physical chemistry has been characterized by high-risk ideas that have paved the way for new research fields, particularly in the development of innovative techniques and methodologies. Wei arrived at Oregon State in 1995 and has held the position of full professor since 2005. She was tremendously successful right off the bat in her career, receiving both an NSF Career Award and a Sloan Award in her first year here. With over 80 peer-reviewed publications, her research has significantly advanced her field. She has also been an influential mentor to numerous students and has secured nearly $5 million of national funding and $1 million from state and OSU sources. Wei's research, which we'll hear more about tonight, addresses a significant challenge in the scientific world: obtaining high-resolution atomic structures of biological macromolecules and nanomaterials. This relies on molecular spectroscopy, which involves the interaction between matter and electromagnetic radiation to generate an absorption pattern or spectrum. This field is used to gather information about the structure or composition of a compound. Wei pioneered a new type of spectroscopy called zero-kinetic electron photoelectron spectroscopy, which, if we don't learn what that is tonight, I will Google it afterwards. This method unveils the intricate rotational motion of an isolated charged molecule post-electron removal. This method is incredibly innovative and has been widely adopted by researchers in the US and internationally. Her groundbreaking work also extends to pioneering an experimental technique involving the orientation of molecules using electric fields and superfluid helium droplets. This method enables the sampling of various orientations, facilitating the creation of a comprehensive three-dimensional structure of molecules. Described by her colleagues as daring, this project, if successful, holds the potential to revolutionize the field of structural biology. Wei's lecture is entitled, "Which Way Up? Using Quantum Orientations to See the Unseen." We're looking forward to your talk, Wei. Congratulations on this well-deserved honor.
Thank you, Eleanor, for the nice introduction. And thanks to the Gilfillan family for such a wonderful donation to the college and to the university. And thank you all for coming in person and on Zoom. And I am truly humbled and honored to be able to deliver this lecture and share with you the past half a century of my life in science and in personal life. So I'll start from the, who's going? I think this is not in the right mode. Oh, I think something is wrong here. It's not in presentation mode. So you might have to close this one. There's another one opening maybe.
Yeah, I already started it for you. Let's go. We need to give you the mic. Or we can use this one.
That may be better. Okay, so now it's working. Okay, yeah. So I'll start from the very beginning to explain my education and training, and then I'll show you some of the work we've been doing since I arrived at Oregon State University. And then lastly, I'll give thanks to where thanks are due. So before we get started, we need to get oriented. So this is the United States of America, and here is the Pacific Northwest. I actually came from all the way across the globe and from a country called China. And this is where I was born. And to zoom in, so my town is here. See, I got to juggle the different pointers. So this is my town. It's about 200 miles southwest of Beijing. And just to get you oriented again, here's South Korea, not enough fingers in the hand, so South Korea and Japan. Okay, the United States prouds itself for its immigration route. But deep down, everybody is interested or curious about where they came from. So genealogy has become almost a national obsession. For a person with a last name Kong, we're 100% sure where we came from. We came from this person from 500 years ago. And there's even a family book that dictates how they name each generation of us. For this reason, the family value is all in education. So we value knowledge and education more than power, more than money, more than social status. Unfortunately, I was born during the year of Cultural Revolution. The educated people are sent to the villages to get re-educated, and that includes high school graduates. So my parents decided that I was going to learn violin because there is a huge shortage of violinists in the country. And one of my uncles were rescued from a village because he knows how to play violin. Apparently, my parents didn't believe in aptitude or gifts because not only couldn't I tell a tone, but also couldn't I count the beats. So luckily for me, in a couple years, the Cultural Revolution was decided to be over. And a year later, a national entrance exam was reinstituted. And a kid like me who have no relatives in upper places, we can do well at the entrance exam and go to college. So guess what I did? I packed up my violin and went back to the books. So in a couple years, I went to Peking University. That's when I was 16 years old. So it was the 1980s, and we were all eager beavers. We loved to study. All of us, we appreciate the opportunity very much. And one of my classes, when I was in junior year, really caught my attention. And so I had this demonstration in the lobby before the lecture. And if you missed it, you can still come after my lecture on the podium, and we can show you how it works. So what's happening here is I have a small hole, and we'll try to pass a laser light through this hole. And what we see is that we don't just see one round spot after the laser passes through the hole. We actually see concentric rings. And if we have two holes, and we would still see the concentric rings, but we see vertical lines. And notice these lines are vertical, where the two dots, the two holes, are actually horizontal. So the lines are perpendicular to the light source. And of course, if we have a matrix or four holes in here, and we would see a similar pattern, but with lots of squares on this image. So this class got me so intrigued, I almost decided at the spot that I'm going to do laser spectroscopy because lasers have one frequency and it has a very single color and it's intense. And what we have just seen is the spatial coherence of the laser beam. So when my boyfriend at the time and now husband applied to University of Waterloo to study surface chemistry, I looked at the brochure he received, and I saw 3 spectroscopists at University of Waterloo looking at molecular properties using all kinds of lasers. So I decided to apply so we can fly together to Canada. So we landed in Toronto Airport, and the next day I went to see Professor Terry Goff in the chemistry department at University of Waterloo. So I thought I was going to Waterloo to do infrared spectroscopy. So in a layman's word, I am going to be using a small hammer, which is the infrared photon, and I'm going to be knocking on this rock, which is the molecule, and then what we're going to do is to try to hear how this molecule rings. That is vibrational spectroscopy. So I went to see Professor Goff, and he said, I'm packing up my lab, and in a week I'll be going to University of Victoria. You can go with me if you like. So for those of you who don't know the geography of Canada, Waterloo and Victoria are two opposite ends of the coast. So that's a very long flight. It's 5 hours. And luckily, Miss Caroline Stars came to see me the next day, and she introduced herself, and she invited me out for lunch. And over lunch, I learned that she works for Professor Hepburn. Professor Hepburn has a bigger hammer than Professor Goff. So Actually, his hammer is so big, he wanted Caroline to smash the rock into smithereens. So then I learned that an organic chemist can be considered an engineer. They put molecules together. A physical chemist is the reverse engineer. We actually break the molecules and try to understand what holds them together. So the analogy, this big hammer, didn't really move me, and I thought that's too violent. And then in terms of science, there's too many degrees of freedom to consider when you put in such a big photon into the molecule. But nevertheless, I went to see Professor Hepburn the next day, and then he said, I am going to Paris tomorrow. But he said, I do have a project if you're interested. And turns out he wanted me to build an even bigger hammer. And this hammer, when it hits the molecule, is actually going to generate sparks. And he calls this hammer extreme vacuum ultraviolet. So the photon is so energetic, it only exists in vacuum. But he said, well, you can still hear the molecule, and you can still see the rotation of the molecule. So just to show you this rotation. So this is a very high resolution spectroscopy. So I thought, well, this is not like playing violin, but at least I should give it a try. So here's a picture of Professor Hepburn right here, and me in the new lab that we constructed, we built with this project. And the reason I joined this lab is that after the lunch with Caroline, she showed me the lab, and my jaw dropped to the floor. Because for every instrument she showed me, almost every instrument she showed me, I had a class or a week of lecture on the principle of this instrument and how it's applied and what are the pitfalls of this instrument. So I decided right there and thinking that working for Professor Hepburn may be more suitable for me than working for Professor Goff. And I understand how this laser works. This is called the ND-YAG laser. It gives out the infrared photons. If you do some magic in the crystal, it makes a green photon. And when these green photons pump a dye laser, they make visible photons. And you do the same trick, visible photons becomes ultraviolet, and that's what you see. And then you combine these ultraviolets together into vacuum in a gas medium, and we can generate extreme vacuum ultraviolet. So this picture is staged. We never worked together like this. Okay, so there's a new kind of spectroscopy on the horizon, and how do we hear about the molecular ringing or see the molecule rotation? And so I'll do this, demonstrate this effect or this type of spectroscopy using a work we've done after I arrived from my postdoctoral position at Cornell University into Oregon. So here is a cluster that we made in my lab, a sodium in the middle, sodium atom in the middle, and 2 ammonia molecules. And we did this by flowing gaseous ammonia through molten sodium. And if we excite this cluster with a yellow photon, we would get the electron out of this neutral cluster. And if we excite the cluster with an ultraviolet photon, we can get the electron out so far, or very highly excited, and then the rest of the cluster looks like just a single charge. And this electron is going to be orbiting around the single charge over and over and over again until an electric field is applied, and then this electron would be ejected out. We can monitor the electron, we can monitor the cation, which is a special name for positive ions, so that's a cation. And so this is what we saw by monitoring the cation. And this work was performed by Peng, a former student, He's now the founder and CTO of a very successful company called Interlight. So let's just recap what we did. We started with a neutral cluster, and we probed it, we excited it with an ultraviolet photon, and then ionized it with an electric field, and we made a cluster. So if you imagine my body is the sodium atom, my hands are the ammonia molecules, and you notice that in the ground state, the ammonia is in this bending operation, so my arms are slanting downwards. But when you take out that electron, the ammonia wants to go horizontal, and suddenly I have this urge to flap my arms. And that's exactly what happened here, and this is the butterfly motion of the sodium ammonia cluster. So we can model this using quantum mechanics. It's a pretty simple model, and we can assign every peak corresponding to the vibration of this cluster, and these numbers represent how fast this cation, this positive ion, is vibrating. And we can also figure out in the ground state, before the excitation, the sodium ammonia cluster is not really sitting steady. And here you can see the green corresponds to the butterfly vibrating with 1 quanta of energy, and then the gold is 2 quanta, and the red is 3 quanta. And of course, most of the cluster are sitting just breathing into the air. So with this result, we thought this is really unprecedented detail. We are really listening to the vibration of the molecules. And it should just take a little more perseverance before we can understand this whole process from the quantum mechanical level. So this is a demonstration in chemistry. There's a classical demonstration in chemistry. So you take solid ammonia, which is cold ammonia, which is in the colorless liquid, and then you put sodium into the ammonia solution, the pure ammonia, and what we get is a deep blue solution. And the reason is the electron from sodium is pulled into the ammonia, and this deep color is from solvated electron. So we grew a cluster, and this is what we saw when we have 4 ammonia molecules attached to a sodium atom. We resolved nothing. And so what happened was this butterfly is flying away too fast. We couldn't capture it with spectroscopy. In fact, this is a known phenomenon, a known fact to most people in the field. And so that's why when I came for my interview at OSU, and I thought I wanted to add in an extra dimension to spectroscopy. So just doing spectroscopy is insufficient to get all the details of the molecular change. I could add a time dimension. I think my colleague Chung Fang is here. But a femtosecond laser costs several $100,000. So I thought I'd go for the cheaper version, which is only a couple $1,000 if you just add an electric field. And the electric field is represented by E, the field strength here. But to get this field to do anything, you got to overcome the molecular rotation, which scales with the temperature of the molecule. So in the end, whether the field is going to have any effect or not, it depends on the ratio between the effect of the field and the rotational tumbling of the molecule. So the colder the molecule, the better for this effect. And when we're talking about fields, there are actually 2 types of electric fields. What I explained earlier is a DC field, is direct current electric field. And there's also another kind of field, it's called AC field, alternating current field. And the laser field is actually an alternating electric field. And this field oscillates and changes the direction at the optical frequency, which is several quadrillion times or 1,000 billion times per second. So obviously, this animation is way too slow compared to the real life laser oscillation. So in a DC electric field, a molecule is going to precess around the field and is actually going to spin around its own axis. And the molecule actually knows its head from tail. The head is the more electron-rich area of the molecule, and the tail is the more positive end of the molecule. In an AC field that is oscillating at the optical frequency, the molecule cannot change its head and tail fast enough to follow the laser field. So in the end, the molecule can only align its long axis along the polarization along the field of the laser. So we call this orientation and alignment. And in the AC electric field, because we can't tell the head from tail, we can only achieve alignment. And when we only have one axis, this is called linear polarization. So, but the AC field has a superior advantage over a DC field, because the AC field can have two axes simultaneously oscillating at the optical frequency. So at any moment, the electric field is actually the vector sum of these two fields. And then this vector sum can trace out an ellipse in this fashion. So this is called elliptical polarization. And if you have just one axis, it's called linear polarization. So when we put an object or a molecule into this elliptically polarized light, and what's going to happen is the longer axis of the molecule is going to align with the longer axis of the ellipse. And then the shorter axis of the molecule is going to align with the shorter axis of the ellipse. So by doing this, we actually prevent the molecule from rotation. The stronger the field, the tighter the control, the better the alignment. So with a laser field, we can actually really hold the molecule steady in space. And so here is a molecular goniometer. So you're holding the molecule, and you can change the polarization or change the ellipse of the laser, and you can rotate the molecule to any degrees, to any angle we want. So here is an example of the results we obtained from this molecule. It's called pyrimidine. And in a DC electric field. So this work was done by postdoc Hongzhi Li and student Karen Castle. And Hongzhi is now a data scientist at Amazon, and Karen is now a professor and chair of her department. And so this work, we tried to use two photons to ionize the molecule. So we collected the cations, the positive ions, as we scan the laser wavelengths, so changing the color of the laser. And the dots are experimental data, and the green lines are calculation. So when you have two electric fields, one is a DC field, this is the one that we added, and the other one, of course, is a laser that we're introducing to the molecules. And so there are two possible relations between these two fields. One is they are parallel, the other one is perpendicular. And the green line I told you is calculation, and here is the equation for that calculation. It took a whole page. It takes a whole page to display the equation, and it's hideous even for a physical chemist like me. So very quickly I realized this equation can be much simplified, and the experiment can be much simplified if we go to a bigger molecule. And so if we go to a bigger molecule, we can define a variable called x, and it's proportional to the field effect and inversely proportional to the rotational energy of the molecule. We can calculate the quantity A in terms of x, and then we can calculate a ratio, and this ratio is the ratio of the intensity we observed when the laser is parallel to the DC field or when it's perpendicular, the two different scenarios I showed you earlier. And this ratio is a function of alpha and A, of course, And then we can see what is alpha in the next example. So this is the results of tryptamine, fluorescence signal from tryptamine. We collected fluorescence, laser-induced fluorescence from tryptamine as we scan the laser wavelengths. And a few sharp-eyed people can recognize who this person is in the audience. So we have two fields. One is parallel, this is a black one, and the other one is perpendicular. And these jags are noises. They're not really signal. They're not rotational signal. And tryptamine has a molecular formula of C10H12 and 2. And even with the same connectivity, there are 5 different ways of arranging the atoms. And we call them the conformers. And we see here each peak corresponds to each conformer. So we don't resolve any rotation, and we don't resolve any vibration, but we have 2 different intensities. We can take the area below each curve from perpendicular, from parallel, and we plot them as a ratio. And so horizontal axis is the electric field, vertical axis is the ratio. You can see only one of the calculations would fit the experimental observation. And the result is we can actually assign the structure of each peak by just that simple calculation. And this angle alpha, I told you earlier, it is the angle between the permanent dipole and the transition dipole. And this angle is unique to each conformation. So by determining this angle, we can actually determine the structure of the molecule without doing any high-resolution spectroscopy, without doing any quantum mechanics. This is all classical mechanics. So obviously, the bigger the molecule is, the simpler the math, the simpler the experiment. So how big can we get to? And these people claim that they can get elephants to fly. So we thought, well, if they can get elephants to fly, we can get them to align. So the question is there any need to align the elephants? Do we want to understand how an elephant is structured? So to answer that question, I packed up my household and we flew to the National Institutes of Health, Washington, D.C., and I spent 5 months there, and then the answer I got was a yes. And I even thought, oh, I better do this as soon as possible to help with humanity. Okay, so why do we want to align elephants? Because we want to understand the structures or dissolve structures of proteins. Why do we want to solve structures of proteins? Because you want to understand the disease mechanism. If we want to design a better drug, the starting point is the structure of a protein. So with the Human Genome Project, we have 200 million proteins that have been sequenced, but only 1,000 of them have been structurally determined. And we do have a whole gamut of technology that determines these structures, but each technology has its pitfalls and its limits. And particularly when we have a type of protein that changes structure when a small molecule binds to it. For example, when a metal atom binds to a molecule to the protein, or when even just an O2 molecule binds to a hemoglobin. So there is a need to develop a new technology, and so this is the technology I dreamed of. We're going to start from here, electron spray ionization. We'll get the protein into the gas phase. So this is where we get the elephants to fly. And then we mass select them and then freeze them in the superfluid helium droplets. These droplets are at 0.4 Kelvin. And this cold temperature will be really helpful for using the laser alignment, as I explained earlier. And they also freeze the protein is conformation. So the protein cannot change its structure once they are inside the droplets. There should be only one protein in one droplet because proteins in this vacuum are charged. And like charges really hate each other. They don't want to be in the same droplet. And all these droplets that containing protein are aligned by our laser field, and then we can shoot the electron gun and generate the images, the projection, the diffraction pattern. And we can do this over and over again. This is a post-experiment until we get a really high image, high resolution image, or a very crisp, good signal-to-noise ratio image. And then we can change the polarization of this laser. We can flip the protein onto another angle, and we take another image. We can do this as many times or as many angles as we want, and eventually we get the three-dimensional structure of the protein. So there are a couple of features to our technology. One is that our electron gun is actually commercially available. We don't need a national facility which costs billions of dollars to maintain, let alone to construct. Our molecules are purified in situ. We have a mass spec before we do the diffraction. So if a small molecule binds to the protein to change its structure, we can determine the structure before and after the binding. And we have no radiation damage, because the protein is only in the electron field for a very short time. We refresh our sample in the repulse. Our detector can be a phospho screen, which is much cheaper, or we can use an expensive one called a direct electron detector. And most importantly, this is a tabletop instrument. And any research-intense universities should be able to afford a couple of them, just like a cryo-EM, and cheaper than a cryo-EM. But nothing is for free. There's no free lunch in this world, right? So there got to be a thing that to give. And the problem, or the extra things that we introduce, is a helium contribution. Because we're trapping the protein in helium, there's going to be a background, and there's got to be something to be done to remove that background. So in a nutshell, what we're trying to do is the exact reverse of this experiment. And recall we had the pattern of light source, and we generate a pattern of diffraction. What we're trying to do is to actually look at a diffraction pattern, and we'll guess where this pattern comes from in terms of molecular structure. So this is the gold nanocrystal, and that's the diffraction pattern we calculated for that aligned gold cluster. So to get this experiment to work is a really daunting task. And right now we have 3 groups of students working on this one. So they're all here today. Joaquin right there is working on the 2nd generation of ion source. Stephen and Kim, they are working on the laser alignment aspect of this project. And a couple years ago, we discovered a special effect with our laser field when it interacts with the molecule. So they're following a clue and trying to maybe add a chapter in the interaction between a laser field and a molecule. And then Andrew and Mauricio are working on the diffraction experiment. So as I told you, there's no free lunch. So how do you handle the helium droplet problem? And we figured out a way. And so this work is done by a former student, Yun Teng. And of course, you see this person again. Yun Teng now is an award-winning instructor in Central Community College in Nebraska. So what you see here on the left is the experimental results of diffraction. When the molecules are not aligned, they generate rings. In this diffraction pattern, we removed the helium contribution. And on the right, you see the diffraction patterns of from the calculation. So we know how to handle helium, the helium background, pretty well. And thanks to Professor Raimel, he actually custom-made a special protein, green fluorescent protein, and we were able to put protein into the superfluid helium droplets. And so we changed the temperature of our source, and we can generate different sizes of droplets. And you can see is the green fluorescent protein doped helium droplets on our detector. And this work was conducted in my group, in addition to the proteins supplied by Professor Mel's group, Maha Ahmadi. She was the student working on this project. Maha is now a professor and chair in her university in Saudi Arabia. A problem with successful students is that they graduate pretty quickly. The new generation has to be trained before they can even pick up the baton and make progress. So when Andrew and Mauricio joined the group, we thought of a simple project to train them. And the project involves putting xenon atoms, rare gas atoms, into a superfluid helium droplets. The experiment was easy. They just finished that in a couple days, including tuning the experimental condition. But it took us several months, more than 6 months, to understand what's going on. And so you can see here, this is the diffraction pattern, diffraction profile. The dotted line, the dots are the diffraction from the experiment after removing helium. And the continuous black line is the calculation. And you look at the residues, they are randomly distributed, and it's pretty small. So that shows the simulation, the calculation is a very good quality. But the reason for this took us so long is that we started with the wrong structure. So we thought when two xenon atoms come together, they are going to make a dimer with a distance of 4.4 angstroms. And that's kind of like a known van der Waals distance for these molecules. And when 3 of them come together, they're going to make an equilateral triangle. When 4 of them coming together, they'll make a tetrahedron. It turns out none of this is correct. And so that's why it took us so long. And so what is the answer? The answer is called a xenon foam. So what's happening in this foam is that in between 2 xenon atoms, there are helium in between. And so this foam structure formed in helium droplets has been proposed more than 2 decades ago by Peter Tunnings, the director for Max Planck Institute. And prior to our work, of course, there was no direct evidence of the formation of foams. And so this is the first time we actually see helium foams or xenon foams forming in helium droplets. So obviously we found the structure, and is it possible to prove it? And at a conference we met a French theorist, Nadine. I can't pronounce her last name. It's Nadine. What is the last name? Whatever. So and Ernesto. So in this simulation, you saw that the helium comes in and it makes a dimer when it's coming in straight. But this time, the helium was coming sideways, and so the xenon is coming sideways, and it has trouble penetrating through the solvation shell of the xenon. So that's the real evidence that this is what's happening. So that's their calculation. All right, so we have a lot to do, and then we still have to put in the laser. We still have to provide the prototype for the first experiment. And then in doing this engineering project, we're also discovering new science. So finally, give gratitude where gratitudes are due. I've been lucky to be a professor. And as a professor, we're always working with people who are in their 20s. They're always in their 20s. All of my students, every single one taught me something about life, about resilience, about compassion, about fun loving. And then I've also been lucky to have a few really talented postdocs. One of them appeared in 2 places, and then the other one has promised he cannot retire until I retire. Okay, lots of collaborators. Some of them we worked, here's Nadine's last name, Halberstadt. Some of them we worked on one project, and others became lifetime friends, mentors, and confidants. And I'm really, really grateful for all this help. And then, of course, The most people I owe my gratitude to, my PhD advisor, Professor Hepburn, and then my postdoc advisor, Paul Houston. And you just saw like Caroline Stars. She's actually a Dr. Stars. She's an instructor at Brock University. Glenn is right here. We just had coffee. He was a mentor since I came on day one. Peter Tunnings is the director for Max Planck Institute, and he's the first one I talked to about this project, and we're still in email communications these days, and I owe half of my career to Professor Beckman. And of course, family, and I think I'm gonna make everybody jealous of me if I tell you how much my husband has done at home. And then my sister, my brother, and then my son, Eddie. And then, of course, we can't forget the funding agencies. Some of them funded just one project. Some of them are decade-long supporters. And we wish this will continue for the next decade. And finally, I'm going to leave you with this video to distract you from asking hard questions.
There are microphones on both sides. If anyone would like to ask questions, come up to a microphone, and I think we can let the people who understood all of the physics and chemistry get things started. Can you come up to a microphone, or if you don't want to, I can repeat the question.
So xenon in helium is just an amorphous phase, essentially, as opposed to a foam. It is everywhere they want it.
Yeah, that's pretty much it.
So
Yeah, they just don't like each other. Their interaction is not strong enough to overcome the solvation shell. The helium is too compact. And there's a calculation that shows the density of helium surrounding a xenon atom. It corresponds to like 17 atm pressure. Yeah.
thank you.
Okay, very quickly. So regarding this xenon, last time I hear your students talk, this was not a theory. So this is great. It's an evolvement of this xenon foam. So my question is why it took like over 2 decades in order to demonstrate it? Is that some experimental challenge that to create this foam? And the second, is this a general phenomenon if you look at other inert gases or some other cases that it will be sandwiched by helium droplets in between?
Use this to answer them.
So the first question is about why there was no other experimental evidence before our work. And the reason is there are no tools. There is no way to figure out how the xenon is compacted or is inside the droplets. And the second question is if this is a general phenomenon among different rare gases. We don't know yet. This xenon is the first one. We did argon. We're still analyzing the data. And it looked like argon is different from xenon. So argon may be forming small compact structures already, but we're not completely sure. So this is not published and not confirmed results. We have the experimental results. The explanation, the fitting of the data is still having problems.
Wei, when you trap proteins, for many proteins anyway, you might have several conformers. And I'm wondering, and they'll be thermally sensitive. Do they have time to re-equilibrate so you only get the lowest energy form in the helium droplet? Or do you have evidence for more than one conformer?
So the situation would depend on what kind of change is going to happen to the proteins in the droplets. So large amplitude motions, real big changes of unfolding is impossible because there's not enough energy to do that. And it actually there's a gas phase experiment right down in Eugene. They're trying to unfold the protein with high energy electrons, and they are really having a hard time doing that because it takes too much energy. But freezes or changes of the branches or the surface side groups are possible when we have the helium quickly cooling the protein when they encounter. So some surface changes are possible, but major changes are impossible.
So on that exact idea, like, what do you think is the ability of this? Because you have effectively single molecule detection here. Would you be able to apply this toward looking at dynamics or heterogeneous systems by, like, you know, somehow separating out different, like, classes of diffraction patterns?
Yeah, that's right. We can do this after we prove the first principle. So yes, there are lots of possibilities to do dynamics. And actually, using X-rays, the ultra-short radiation from free electron lasers, there's actually one group. They're exciting the protein with a photon, a femtosecond photon. And then they're looking at diffractions from these proteins. But the proteins are in nanocrystal, and it breaks or it explodes after each probing pulse. So, and this technology is called diffract and destroy. So once you diffract, you destroy the protein. And with that technology, it's possible. But the limitation of that technology is a nanocrystal. You have to be able to see a good enough picture from each sample. And that's impossible when you have just a single molecule.
Wei, thank you. I'm interested in the polymer. So you said it's custom made. What is your requirement for Dr. Mayo in terms of that polymer? Why you need that polymer?
Oh, it's just a green fluorescent protein, and then we needed a polymer. We needed the custom-made protein because we're going to do the alignment of the protein and trying to figure out how well the green fluorescent protein is staying in the droplet. But we end up not doing that in the end. So that's the custom side of the protein. So we really just need a wild type green fluorescent protein for this experiment.